the auxiliary equation, 1 times m minus 1. You recall that because it's from the solution pattern as y equals x to the power m. So y prime is m x to the m minus 1. Y double prime is m times m minus 1 times x to the m minus 2. So the coefficient of its derivative as part of the auxiliary equation. So 1 times m minus 1 plus 1 times m, and then plus the lambda equals 0. Simplify to be m squared minus m plus lambda equals 0. That's nice. So m and minus m cancel. To get m squared plus lambda equals 0, or m equals plus minus square root negative lambda, which is the same as the first example. So case 1. So negative lambda positive is 2 real roots. Okay, negative lambda positive, or the lambda is negative. With this, introduce the omega square as negative lambda. So then the m gonna be plus minus omega, and the general solution the Cauchy Euler equation, the solution is in the form of the x to the power, right? X to the power. So general solution is y equals c1 x to the power omega plus c2 x to the power negative omega. Just depends on what type of equation that you are working on. Now, from this general solution, again, use the conditions y prime at e to the negative first equals 0 and y at 1 equals 0. That means we're going to need y prime. So on the side here, y prime is C1, since omega is real number, right? Real number. So C1 omega x to the omega minus 1 minus C2 omega x to the negative omega minus 1 as a y prime. So bring it to the part to find the C1 and C2. At e to the negative first, y prime is 0. So 0 equals C1 omega x to x is e to the negative first to the power omega minus 1 and minus C2 omega times x e to the negative first to the power negative omega minus 1. And for the second condition, y at 1 equals 0. 0 here, back to the y equation, which is C1 times x, which is 1. So gonna 1 to the omega is going to be the same as 1. So C1 plus C2 equals 0, or C1 equals negative C2. We place it in here in the first equation, which is from the first condition. So then we get 0 equals C1 as a common factor, and also omega, and e to the negative 1 times omega, negative 1 times negative 1, which is negative omega plus 1, plus e to the same way here, omega plus 1. Omega is greater than 0, exponential greater than 0, greater than 0, for C1 to be 0 as well as C2. This is the part that I'm looking for. I know it's going to be trivial for the lambda less than 0. For the not the for the case 1, for the real 2 real roots. So you just use whatever the knowledge or the understanding that you have from chapter 4 to analyze the problem case by case. So then C1, C2 equals 0. This case is gone. So trivial solution for lambda less than 0. All right. Case 2. We have is m equals plus minus square root negative lambda. Case 2 gonna be the repeated roots. Repeated roots, only case that repeated root is gonna be the case that the lambda equals 0. If lambda equals 0, we have m equals 0 and 0. So then the general solution sorry. Y equals C1 x to the 0 plus C2 x to the 0. What happens for the Cauchy Euler solution if we have the repeated m's? We multiply by natural log x. Right? That's the difference between the Cauchy Euler and the constant coefficient equation. Or we can write y as C1 plus C2 multiplied by natural log x. Right, next, we're gonna find C1 and C2 using the conditions y prime at e negative first equals 0 and y at 1 equals 0. And set aside again, the y prime is derivative C1 is 0. Derivative of the second term is C2 times 1 over x, or just C2 over x. Then the y prime equals 0 for x as e to the negative first. Yes, this one not 0. For C2 to be 0. Y at 1 is 0. C2 is already gone for this case. So y, that's C1 is 0 no matter what. It doesn't matter what the number is. Again, another trivial solution. Just different cases to make it trivial solution for lambda equals 0. And the last hope is for case number 3. From the solution, m equals plus minus square root of negative lambda, we need the complex solution, or the complex solution, or the conjugate complex. So this case, the lambda has to be positive. So we need omega square as a helper to replace the lambda. So then the m equals plus minus omega I. So the solution is y equals, we call the x to, for the pattern, it's going to be x to the power 0, and then the sine cosine, right? Let me see, 1 cosine omega natural log x plus C2 sine omega natural log x. All right. And then for this case, we're going to need y prime. Go ahead, find y prime. The derivative of the cosine is negative sine using the chain rule. Omega is the coefficient, the constant, so multiplied by omega divided by x. Okay, and then plus, same thing, plus C2 cosine, this time omega natural log x times omega over x. First condition, y prime at e to the negative first equals 0. Second one, y at 1 equals 0. The first condition, 0 for the y prime, and replace it negative C1 sine of omega natural log e to the negative first times omega over e to the negative first plus C2 cosine omega natural log e to the negative first is kind of tedious, right? And then for the second one, y at 1 equals 0. Let me see one cosine of omega natural log 1, which is 0. And plus C2 sine of omega times 0, which is 0 again. So sine 0 gone. Cosine at 0 is 1. That means C1 is 0. Right. For C1 to be 0, this term goes away. So force this one to be gone. And now we have the condition that the C2 times cosine and natural log e to the negative first is -1. Right? It's -1. So gonna be negative omega multiplied by omega over e to the negative first. If we look for the case that C2 not equal 0, we're gonna make this product to be 0. And also the omega itself is positive number, e to the negative first positive number as well. That means we just look for the case that the cosine of negative omega to be 0. And the trig function, recall this is the cosine, note here, note the cosine theta is the same as cosine of negative theta because the cosine is an even function. Even function. That means instead of looking at the case of negative omega, we look at the case of the cosine omega itself equals 0. What angle that the cosine gonna be 0? Note that omega is positive, right? So omega gonna be what? Pi over 2, 3 pi over 2, 5 pi over 2. You guys follow? So pi over 2, we look for the positive angle. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. And with this, we can rewrite it as the odd multiple of the pi over 2. The odd multiple is the 2n as an even, and then plus 1 to make it odd. Multiple of pi over 2. For n equals, if you do 2n plus 1, we include the 1 here, right? So n gonna start from 0. So depends on the form that you put in, but the index has to satisfy whatever from the original form. Okay, so omega is 2n plus 1 pi over 2 for n equals 0, 1, 2, and so forth. The omega square is the lambda. So then this gonna give us the case, the lambda n, which is omega squared, gonna be the quantity 2m plus 1 square times pi squared over 4 as the eigenvalue for n equals 0, 1, 2, 3, and so forth. We got eigenvalues, and next we're gonna get eigenfunctions associated to the lambda n. So then going to be the y equals, from the y form that we get as a general solution, the C1 is 0, the cosine term is gone, right? So gonna keep only the sine 1. So the yn, or the corresponding eigenfunction for each eigenvalue, is in the form of the sine of the omega, which is the odd multiple of the pi over 2 times natural log x for n equals 0, 1, 2, 3, and so forth.